Okay, folks, here we go. This is my first attempt at trying to record some answers for the paper 1B. I'm going to apologise in advance for all of these videos. I've done it by hand and I've not had a lot of time to do this, so my writing is particularly bad here. However, I can talk you through this one. I've even forgot to check which paper this is, but just check the title of the video and it should match up. So, the idea here is that you should have done the question and then you can go through the answers. I'm really just trying to give a bit more of a commentary as to what's going on here rather than just using the mark scheme, because I know that there's a lot to think about here, and there's a lot of sort of niggly bits inside the paper 1B which you need to pay attention to. So we'll start with this question. We're looking at the resistivity of a metal in the form of a cylindrical wire. That's important for later. And we've got the following measurements. We've got the length of the wire L, which is 462 millimeters, readings of the diameter D of the wire, and then we know the resistance of the wire. Okay, so you're told this here. First thing I would say to you is have a look there. We've got uncertainties and uncertainties. We are going to be doing something with uncertainties in this question. You know that purely because of what you can see on the screen. Okay, now we're asked first to outline why we've made multiple measurements at different places. Okay, and this is really, if we can understand this in different ways, explain this in different ways. The main way I would explain that is to account for something called random error. And what that means is that the wire will not be made perfectly. There will be some random deviations from the sort of set value. You can imagine there's a machine which is trying to machine this in a certain way. Okay, it's going to have random error, and we account for that. And we would, as we'll do later, account for an average. Now at this stage, I'm going to point out in the data, we've got different values here. Notice I've circled this one here. This is an anomaly. This is a bit of data which does not fit the pattern. It's too far away from everything else, and it's something to look out for anytime you're analysing data sets like this one. Okay, so we're then going to look down in terms of the next bit. This is really quite a nice set of marks. You'll notice in paper 1B, I think there's some horrible marks and there's some lovely ones, and there's nothing really in between. Lovely marks here. All we want to do is suggest suitable instruments for measurement of L. Well, L is a length. I suppose the tricky bit here is expressed in millimeters, so it's 462 millimeters. Okay, that's 46.2 centimeters, which is less than a meter, so a meter rule would be suitable. Please never write a ruler here. A ruler is not really, we never really use ruler as an answer. It'd be a meter rule or a half meter rule even, but not a ruler. For D, we're going to use a caliper, okay, a vernier caliper. We want to be super, super technical, or a micrometer, because they're measured to small values. We're looking at millimeters here. So again, I think of our first 3 marks. Remember, we're looking at 20 marks in total for this paper, 3 out of 20. That is a really nice start there. That's 15% of the paper. Okay, we're then going to shoot across, and I really hope this works on the screen. Apologies if it doesn't, to the slightly more mathematical bit. So we are asked, let me just grab this. We are asked now to show that the mean diameter of the wire is about 0.2. Now what I've done here is I've taken my data from that first table, but I've only taken the 5 values. Remember I identified that anomaly? Well, the anomaly has to be left out here. Why? Well, because it really skews the results, okay? So if you notice a bit of data that doesn't fit, you can confidently say, you know what, this doesn't fit with the rest of it. I'm not going to consider this in my calculations. What we then do is we calculate our mean, and we get a 0.99 over 5, 0.198, which is basically 0.2 millimeters. Why is that important? Well, if you included the anomaly, which a lot of students do, you actually get a number which is a bit bigger than this, and it's there we have a bit of a sort of a dilemma, because it's close to 0.2, but it's not very close. Okay, 0.2 is a very small number. We need to be pretty close there, within 10%. And so actually, you probably end up saying that a number that's not technically close enough is equal to this. Okay, so the taking out of the anomaly is important here. We're then asked to calculate some fractional uncertainties. Okay, in this case, if we sort of zoom back, we can see here we don't know delta D, but we know the range of values. Okay, so we're going to firstly calculate delta D by using half of the range. If you've got multiple values, that's the way we do it in physics. No standard deviation or anything here. Our maximum value is 0.22, our minimum 0.18. So we have a 0.04, and we end up dividing by that by 2, half the range, 0.02. Now, I think a lot of students would forget to divide by 2 here. Remember to make sure you divide by 2 there. Okay, we're asked for the fractional uncertainty. and that's delta D over D. We're going to use a 0.02 over our 0.18 or a 0.2, which gives you approximately 0.1. That's basically 10%. Okay, so we've got 10% there. All right, you're then asked to calculate the fractional uncertainty in the length of the wire. This is quite a nice question. Okay, we are told these answers in the original question. I won't scroll back just yet. Delta L over L, we were told 2 millimeters over 462. That gives 0.00432, which is about 0.43%. Now, why have we been asked to do all that? Because they're leading you up to this last question, right? And again, this is where my working is disgusting. I'm really sorry. I've done this on a tiny piece of paper, but I hope it makes sense. Resistivity is RA over L. Okay, A is the cross-sectional area, and that is going to be a cross-section of a circle. And we want to calculate rho and give its absolute uncertainty, and then we are asked to state our answers to the appropriate number of significant figures. You will have seen this before if you've done any questions like this. You want to do things appropriately, so let's do this now. We're firstly going to calculate rho. That's RA over L. We know R from the previous part of the question. We know L from the previous part of the question. The main thing is we have to make sure we express in meters. The bit we don't know is A. A is a cross-section of the wire. That's a circle, so we're going to do pi d squared over 4. Why d squared and not r? Well, because we've measured d. That was our 0.2 millimeters, which I've got in here. So we're going to process through the numbers, and I'm going to just trust that you can read here. We've got 13.7 r times pi. We've got our 0.2, that's our d squared, dividing by 4 from this pi d squared over 4. And then we're divided by 462 times 10 to the minus 3. And we end up with this number, 9.32 times 10 to the minus 7. Just so you're aware, okay, resistivities tend to be around about these kind of 10 to the minus 6, 7, 8 kind of values, so that seems suitable. So I'd get a mark for that, okay? I then get a mark for thinking about the uncertainties. Delta rho over rho is going to be delta r over r plus delta a over a plus delta l over l. This is a multiplication and division. It's a really good example. So we're going to add together the percentage uncertainties effectively. All right. We knew delta r over r from the beginning of the question. That was 1.5%. Delta a over a is a little bit harder. We don't know delta a over a, but we know delta d over d. Delta a over a is going to go with delta d squared over d squared, and that's 2 times delta d over d. This is the bit that students find tricky. Remember, if you've got delta d squared over d squared, we take the n and we multiply delta d over d. All right, that's going to give us 2 times 10%, which is going to give us 20%. We're going to add those percentages together. We've got 1.5 from R, 20% from A, and then a 0.4 that comes from our delta L over L to give 21.9%. And we're then going to calculate delta rho. We know the fractional uncertainty. We know the value of the resistivity itself. So we're just going to multiply that 0.219, that's 21.9%, by the actual value to get a number which is 2.04 times 10 to the minus 7. That is a lot of work for 1 mark, okay? I'm sure there's room here for errors carried forward, etc., etc., etc. So, for example, if you got this wrong, that would mean you calculate delta rho wrong. However, you wouldn't be penalised again for that. The bit that you really need to pay attention for is presenting your answers to an appropriate number of significant figures. Now, what does that mean is, well, our uncertainty must be to 1 significant figure. So this 2.04 has to be expressed to 1 significant figure, and 2.04 to 1 significant figure is just 2. So our uncertainty becomes 2. The value itself then needs to be modified so that the uncertainty comes in the least significant digit. So I started off with a 9.32. I would then be saying 9.32 plus minus 2. Well, that doesn't make sense. I've got this 0.32, which is completely nonsensical. So I'm going to reduce that now so that my decimal places match. In this case, I have no decimal places. So therefore, both answers are given to 0 decimal places, 2, and then we've got 9.32 to 0 decimal places, which is just going to be 9. And so your answer changes quite significantly. We go from this 9.32 plus minus 2.04 to 9 plus minus 2 times 10 to the minus 7 ohm meters. Now this analysis comes up again and again and again. You're always asked to present your data to appropriate significant figures, so I really suggest it would be something that you practice before your paper 1B.